In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about nuclear fusion with the respect to relativistic coupling in the same physical systems as considered in the previous subsections. Nuclear oscillating a different interaction is expected to apply as well. Relativistic coupling results from the fact that oscillating nuclei in the lattice undergo Lorentz transformations, which implies a coupling between its center of mass motion and internal nuclear degrees of freedom. See section 6.7 and reference 93 for more details about this coupling mechanism. For relativistic coupling, in the indirect coupling exchange between a deuterium-deuterium and helium-4, door transitions assumed to start out in the excited state, for example, as deuterium-deuterium, and a deuterium-deuterium helium-4 receiver transitions assumed to start out in the ground state, for example, as helium-4. We have equations 114. U relativity 6 to the power of 2 is equal to phi helium-4 absolute of phi helium-4 multiplied by c to the power of 2 p helium-4 multiplied by phi deuterium-deuterium absolute of multiplied by phi helium-4. See sections 6.15 for a derivation of the terms which yields here. Given for characteristics phonos, U relativity 6 to the power of 2 is equal to 0.0362 square root nu nuclear divided by nu molar e to the power of minus g to the power of 2 c to the power of 2 square root m deuterium m helium 4 divided by n p d set tau r, where the variables are the same as in the prior subsections. Note that the masses m deuterium and m helium 4 are essentially the same as far as the phonos are concerned. We call that the minimum rate starting rate in equation 78. Gamma minimum is equal to 2 divided by h, 2 absolute 1 minus eta Vj to the power of 2 divided by delta mc to the power of 2 square root n addition temperature n helium 4 plugged into the U relativistic to the power of 2 for Vj to the power of 2 yields gamma mean is equal to 4 absolute 1 minus eta multiplied by 0.0362 square root nu nuclear divided by nu molar multiplied by e to the power of minus g to the power of 2 square root m deuterium m helium 4 c to the power of 2 divided by delta msc to the power of 2 multiplied by p this tau r divided by h multiplied by square root n deuterium and helium 4 divided by n. To evaluate these expressions, we need to consider the values of the all relevant parameters. We take absolute 1 minus n, 1 minus eta is equal to 0.1. Nu nuclear divided by nu molar is equal to 6.65 multiplied by 10 to the power of minus 12. G is equal to 90.35, where the volume ratio and gamma factor are for the Petri state, and where absolute 1 minus eta is for the deuterium divided by 3.1. Helium-4 contribution to the deuterium helium-4 transition per section 6.5. Moreover, per the section's introduction, and deuterium divided by n is equal to 0.001 multiplied by 0.25 multiplied by 1 divided by 9, and helium-4 divided by n is equal to 0.01, where we assume a loaded lattice where every 1000 unit cell contains a deuterium molecule, and where 25% of the deuterium molecules are in the Petri state. See figure 38 in section 6.1, with only one of the 9 possible Petri states with J is equal to 1 being involved in the R multiplied by CP transition. See section 6.9 and 6.8, and where every 100 unit cell contains a helium-4 nucleus. We choose experimentally plausible values for vibrational power dissipation and frequency applied to the lattice as PAD dissipation is equal to 1 watt and frequency is equal to 5 megahertz. which gives a final lifetime of the tau r is equal to 10 to the power of minus 12 multiplied by 10 to the power of minus 7. Frequency of r divided by 1 megahertz to the power of minus 3 divided by 2 seconds, which is equal almost equal to 0.003 seconds. Evaluating the rate expressions based on the above values results in a minimum transfer rate on screen of the tau gamma minimum on screen is equal to 2.32 multiplied by 10 to the power of minus 63 1 per second. Since we use the on-screen gamma or factor g above, we can consider the effects of screening by multiplying with per section 6.3 e to the power of 2 delta G screen, where delta G screen is equal to 49.2. Accounts for electron screening of the Petri channel of the deuterium nuclear wave function with 350 electron volt screening potential. See section 6.3. This result is uh, gamma minimum screen is equal to 1.26 multiplied by 10 to the power of minus 21 per second. To obtain the maximum rate, peak rate of the decay enhancement pulse, we apply the additional decay enhancement per section 5.2. Gamma maximum is equal to gamma minimum 1 divided by 4 and a deuterium 4 and a deuterium is equal to 10 to the power of 15. This yields gamma maximum screen is equal to 3.15 multiplied by 10 to the power of minus 61 per second. Again, this is the population level transfer rate. For example, the rate at which the ensembling group A transfer excitations to ensembling group B to obtain a rate per deuteron pair that is comparable to the semi-estimate given by Konin and Nuremberg 1989 in reference 20. We normalize the expressions. Taking the decay expression, enhanced expressions, we obtain gamma maximum screen divided by n deuterium is equal to 3.15 multiplied by 10 to the power of minus 21 1 per second. Such a rate estimate means that this kind of excitation transfer would get into the observable range. Let us therefore also consider the minimum rate per deuterium to get a better sense of whether the process of time evolving with decay factors from the minimum to the maximum rate has a chance to get started. Gamma minimum screen divided by n deuterium is equal to 1.26 multiplied by 10 to the power of minus 35 1 per second. Several points can be noted here. We can see that the estimated transfer rate based on the relativistic coupling is substantially faster than the obtained rates for magnetic and electric dipole coupling. However, these rates are still not in the observable range, while the maximum rate per deuterium pair outcompetes the spontaneous rate from Konin and Nuremberg 1989 based on the reference 26 sections 6.3. The minimum rate per deuterium pair doesn't. Note also that the time evolution of decay factors has to take place within the constraint of the decoherence time of the system. We provide an estimate for the decoherence time in section 6.21 yielding a value of about 1 nanosecond. Comparison of coupling stage, the calculation in this section suggests that the maximum rate for cooperatively enhanced resonance excitation transfer based on the relativistic RCP interaction is orders of magnitude larger than what would be expected from the DE and micro B interactions above. However, R rates estimated in the sections are below the observable range as discussed in the introduction and as can be seen from the equations 79 and 76 as well as figure 13. A major hindrance factor is the transition through the Colombo barrier that occurs twice per each transfer, once for the deuterium molecule tunneling inward to the helium-4 states and once for the helium-4 nucleus tunneling part to the deuterium state. After this exercise, the fastest transfer that we consider to be relevant to experimental reports of observable rates will be considered in the next sections. Now I want to go through the next chapter 5.4 Palladium nuclear receive as a receiver system. In addition to helium as a receiver nuclear discussed in earlier sections, Heavier lattice nuclei can be considered as candidate receiver systems for the transfer of excitation from deuterium-deuterium. It is not likely that such nuclei exhibit excited states precisely resonant with deuterium-deuterium helium-4 transitions at 23,848,109 electron volt hours. Several lower energy transitions can be resonant with the deuterium-deuterium helium-4 transition, as will be discussed in detail in sections 5.7 and the subsequent sections. Comparatively small energy differences can be made up via energy exchange with oscillator modes when the system first starts up. After the system's startup, the receiver system will have more energy, so that states at high energy in the vicinity of multiple deuterium-deuterium helium-4 transition energies can be accessed, where the density of nuclear molecular cluster states can be high, as will be discussed in the sections 5.10 in more detail. Significant energy exchange with optical phonons and plasmons looks to be possible under conditions where the density of states, including states from multiple transitions, is high, and when the phonon mode or plasmon mode that is cooked to the and emitted into the is highly excited. This section provides an overview of nuclear excited states available in a palladium lattice. Also, most points raised apply to other elements as well. Natural palladium contains six stable isotopes: palladium 102, palladium 104, palladium 105, palladium 106, palladium 108, palladium 110. So excited states from all these isotopes can be expected to be amply available in the palladium lattice. When seeking to identify states suitable for nuclear excitation transfer dynamics in mid-sized nucleus such as palladium, two categories of nuclear excited states are candidates that are discussed here. First, there are nuclear bond states, and second, there are nuclear cluster states. We will begin with an overview of nuclear bound states in palladium isotopes and then proceed with an overview of nuclear cluster states with a focus on nuclear molecular states, which represents a comparatively long-lived subset of nuclear cluster states. These sections conclude with a discussion of key properties that make candidates excited states suitable as participants in nuclear excitation transfer dynamics. Now you see the palladium bond states. Figure 15 shows non-nuclear bond states for stable palladium isotopes from the nuclear deuterium database. Nuclear bond states have been widely studied for many isotopes with aggregated data on corresponding energy levels, lifetime, and transitions. Publicity available in nuclear databases such as nuclear data, noun bond states of the stable palladium nuclei from nuclear data are shown in figure 15. Above the neutron ionization threshold in the 7 up to the 10.5 megaelectron-volt range depending on the palladium isotope. The bound states are quite unstable against neutron decay above the proton ionization threshold in the 7.7 up to the 10.5 megaelectron-volt range, again depending on the isotopes. The bound states become increasingly unstable against proton decay. Similarly, above the alpha ionization threshold in the 2.1 up to the 4.4 megaelectron-volt range, depending on the isotope. The bound states are unstable against alpha decay. Again, the more unstable at the higher above the ionization energy of proton, neutron, and alpha removal energies are tabulated in section 6.17. The relativistics ACP interaction is a tensor operator with a magnetic quadrupole selection rule. See section 6.8. And when considering palladium nuclear as receiver systems for nuclear excitation transfer, we are interested in decay enhanced transitions from the ground states of the stable palladium isotopes. If the energies, lifetimes, and multipolarities of transitions coupling to the ground state were available for all of the palladium bond states, then we would be able to simply make use of the databases to compile nuclear data with which we could analyze the excitation transfer schemes of interest. However, the datasets of nuclear bound states are not complete. The density of nuclear bound states increases with energy, but the density of energy levels in the canonical nuclear databases, such as the nuclear DAT, don't follow this expected relationship for levels above about 3 mega electron volt. This is because at present techniques are lacking to study excited states efficiently and systematically. In addition, there have been no important applications to motivate such studies until now. The nuclear bound states of some isotopes have been studied more comprehensively than is the case with the palladium isotopes to date. We draw attention to the bound states of SN120 as reported in the reference 94. An energy level diagram is seen in figure 16. Here we can see that the density of the states increases with energy as expected. This suggests that fewer states are missing from the dataset since the number of nucleons in SN120 nuclei is similar to that in palladium isotopes. We can derive important lessons from the SN120 database for palladium nuclear as will be laid out below in palladium nuclear datasets. Figure 16 illustrates non-nuclear bond states for the SN120 isotopes. Now I want to go through the palladium bond states with M2 transitions to the ground states. Nuclear level diagrams have been developed from experiments involving radioactive decay from the neighboring isotopes and from the experiments involving neutron, proton, and alpha irradiation. Most of the transitions between the ground states and excited states at a few mega-electron volt or electric quadrupole E2 transitions, which tend to yield large signals in accelerator-based measurement campaigns. There are fewer electric dipole E1 transitions, but these are generally easy to detect as well. The transitions of interest to us involve weaker magnetic quadrupole M2 coupling with the ground states, which tend to be excited less efficiently in collision. Moreover, M2 gamma lines tend to be weaker because electromagnetic quadrupole coupling in radiative decay is a relatively weak higher order effect, and as will become clear later on, we are interested in weak M2 transitions, which are in general even easier to miss in an experiment. Consequently, it is likely the case that the transitions that are of particular interest are severely undercounted in the databases. M2 radiative decay, as will be discussed in more detail in sections 5.8, coherent nuclear dynamics, are most efficient in the case of excited states that are reasonable states. That this is the case because quantum coherence is degraded or lost when an excited state decays. Coherent dynamics are fastest in the case of the transitions that have a strong coupling. However, there is a trade-off. The strength of coupling relevant to the coherent dynamics is proportional to the square root of the normalized transition strength, square root omicron to the power of 2, which can be expressed through a dimensionless coupling constant V almost equal to omicron, whereas spontaneous radiative decay rate is proportional to normalized transitions stage, which is the omicron to the power of 2. Gamma M2 is almost equal to 2.2 multiplied by 10 to the power of 7 or to the power of 2 divided by 3, epsilon divided by 1 mega electron volts to the power of 5, omicron palladium to the power of 2, 1 per second, with gamma M2 being the Y scope scale by the transition strength, which will discussed further below. For more background, the normalized transition strength omicron to the power of 2 sections 5.8 and blue transitions that might be assumed to be particularly suitable for coherent dynamics in the model present here due to their strong coupling strength are also the transitions which will suffer the fastest radiative loss. This competition between the coherent and radiative dynamics and its impact on the nuclear excitation transfer at large will be discussed in greater detail in sections 5.8. To estimate how fast this radiative loss might be, we can make use of bioscope estimate for radiative decay. The Weisskopf estimate for radiative decay is grounded in the concept of single particle transitions, assuming that the transition matrix elements are primarily determined by the motion of a single nucleon. The model incorporates basic assumptions about the nuclear structures, such as the spherical shape of the nucleus and the use of the harmonic oscillator wave functions for the nucleons. It calculates transition probabilities by considering the multipolarity of the emitted radiation, for example, electric dipole, quadrupole, and derives the standard transition rates for each type of multiple radiation. Weisskopf estimates for the radiative decay rate for M2 transitions are shown in figure 17 for the six stable palladium isotopes. Later on, we will make use of this estimate when determining the minimum excitation transfer rates from the deuterium-deuterium helium-4 transition needed to outpace the coherence processes and to get coherent dynamics into a stable regime. This is in addition to an estimate for the deuterium-deuterium decoherence time, which is on the order of 1 nanosecond. Inspections on figure 17 indicates that even tau M2 transitions are not strong if fully allowed. The transitions are sufficiently fast so as to impact the coherent dynamics when the transition energy exceeds 1 megaelectron volt. Given that there are very few M2 transitions at or below 1 megaelectron volt, this suggests that we are interested in weak M2 transitions at higher energies. As its name indicates, the Weisskopf estimate of the state's lifetime is only an estimate. Actual lifetime depends on the particular dynamics of nucleus transition, which can go far beyond the comparatively simple considerations underlying the Weisskopf estimate. We capture the dynamics that the Weisskopf estimates fails to estimate, and in a normalized transition strange omicron to the power of 2 that satisfies mm, with respect to relativistic coupling and associated transitions, the O factor can be taught as the square root of the normalized M2 transition range for the transition. Since our knowledge of how big these transitions matrices elements are in the palladium isotopes is limited, we will express matrix elements and rate in terms of omicron values as so as to explicitly distinguish between transition and specific differences. Consequently, if a transition is particularly big and its lifetime is underestimated by the Weisskopf estimate, its associated omicron value would be less than the 1. Data set for E1 transitions in SN120 in Musher and his colleagues 2022 in reference 94. A list of the 249 energy levels are given for SN120 along with estimates for the associated electric dipole E1 transition strength. We might expect there to be a similar distribution of levels and transition strengths for magnetic quadruple M2 transitions in the stable palladium isotopes. We use the SN120 dataset in place of stable palladium isotopes where we estimated transition strength according to the BE1 is equal to omicron to the power of 2 e to the power of 2 FAM to the power of 2. The resulting distributions of omicron values and energies are shown in figure 18. Figure 18 illustrates transition strength of omicron values extracted from the Musher and his colleagues in 2020. Based on the Musher work, you see that the x-axis we have electron based on the mega electron volt, and in the y-axis left side we have omicron, and the right side we have a count as a histogram. Cluster-based nuclear molecular states. Earlier efforts to study the possibility of excitation transfer among ejected nuclear states ran into the difficulties due to the lack of reasonably stable states near the deuterium-deuterium fusion transition energy at 23.85 megaelectron volt. A possible solution to this problem lied in the recognition that reasonably stable high-energy states can form as so-called nuclear molecule states. A specific type of nuclear cluster states in some metal hydrogen experiments observations that suggest fission-like transmutations of lattice nuclei has been reported. If coherent nuclear dynamics can result in the excitations of reasonably stable and highly excited nuclear molecule states, and if this nuclear molecule states decay by tunneling that would be represents the basis of the possible explanation for such report. This motivated the development of the liquid drop model codes with which to calculate nuclear formations, leading to the realizations that the models used for deformed nuclei in exciting fission and fusion literatures don't predict reasonably stable non-rotational nuclear molecules in the stable palladium isotopes. A solution to this problem involves the notion of the nuclear molecules based on the cluster, where two or more cluster remains nearly stationary at short range. In liquid drop models, there is no significant potential barrier keeping nuclear cluster apart, so one daughter can move into the other daughter easily. In a binary nuclear molecule in a liquid drop model calculation. However, in more sophisticated cluster models, there is a barrier. This suggests the possibility of nuclear molecules cluster states in palladium isotopes where daughter parts of a nucleus are held close to their parents by strong force interactions, but where a potential barrier prevents them from the coalescing. In the literature, such nuclear cluster states have been considered in the conjunction with carbon-12 nuclei that can form molecule-like states of magnesium-24. Calculations down for such states suggest that the existence of reasonably stable nuclear molecule states that involve separated clusters rather than extreme nuclear deformation. The idea is that the daughters remain localized as a separate unit with essentially no net relative kinetic energy, and illustrations of a few cluster states in magnesium 24 from a recent paper of Otsley and his colleagues in 2022, reference 95 is shown in figure 19. Work so far on these states has focused on the low mass nuclei where the relevant experiments data exist. We conjecture that this kind of nuclear molecule cluster states also occurs in the palladium isotopes. Nuclear cluster states are much less studied than nuclear bound states, and no comprehensive database exists. We were interested in understanding at what energies relevant nuclear cluster states might occur in the palladium isotope, and also how stable they might be against tunnel decay. For this, we developed a simple model for binary nuclear cluster states that consist of spherical daughters with surfaces separated by zero point 0.5 picometer, with a total energy that corresponds to known mass energies from isotope mass tables, and with a folded Colombo and strong force contributions from the finite range liquid drop model. This model is discussed further in section 6.20. So we are watching the figure 19 illustrates a live diagram for magnesium 12 depicting highly excited nuclear molecule cluster states from the Astley and his colleagues in 2022 reproduced with permission. Note that the indicated level positions for the nuclear cluster states only include the mass energies with no inclusion of the binding energies, which will be several mega electron volts. Excited states energies predicted from the model are illustrated in figure 20. The more symmetric nuclear molecule cluster states generally appear at higher energy as a consequence of large Colombo repulsion, with substantial spread in energy due to the differences in the individual cluster mass energies. Highly unstable ground state palladium isotopes can have significant extra mass energy at lower energies that are more asymmetric. Binary clusters, including clusters of RH and hydrogen isotopes and Ru plus helium isotopes for illustrative purposes. We will refer to Ru plus helium states as exemplary nuclear molecule states. Later in this text, the model predicts more than 1,000 non-rotational binary cluster states. The associated density of state as a function of tunnel plus beta decay lifetime is shown in Figure 21. Note that many of these binary nuclear molecule states are predicted to be quite stable against tunnel decay, with tunneling times will in excess of 1 second. In future work, we seek to refine such models and extend them so as to allow for estimation of a matrix elements connecting these states to their ground states. Simple forms of resonance excitation transfer require a precise energy match between the initial state transition and a final state transitions. More complicated generalized resonance excitation transfer require a precise energy match between a possible combination and initial state transitions and a possible combination of final state transitions. Yet more complicated models of excitation transfer allow for energy exchange with the oscillator, in our case plasmons and phonons, to make up for energy mismatch. The interest in states with energy levels close to the energy of the donor transitions, for example 23.85 megaelectron-volt, motivates an interest in nuclear molecular cluster states more complicated than binary clusters. Such variations of nuclear molecule states offer many more configurations, and therefore states in region of interest most easily visualized are binary nuclear molecular cluster states with two daughters. However, the concept extends to more complicated ternary and tertiary nuclear molecular cluster states. A collection of different cluster configurations is illustrated in Figure 22. So Figure 20 illustrates a molecular deuterium-deuterium and ground state helium-4 levels along with naive, non-rotational and non-vibrational binary nuclear cluster states up to 70 megaelectron-volt of the stable palladium isotopes. Figure 21 illustrates distribution of nuclear molecular cluster states lifetime by order of magnitude. Now I want to go through the excited palladium storage states and different nuclear excitation transfer schemes. The question is now, what would be required to extend the notion of resonant nuclear excitation transfer as developed in 5.1, 5.2, and 5.3 to include palladium nuclei as a receiver system? This situation would be conceptually simplest if all of that was required was to find a reasonable, stable, highly excited palladium star state that is precisely matched to the deuterium-deuterium helium-4 fusion mass energy. In the hypothetical case, the previously introduced model of excitation transfer based on simple second-order excitation transfer could be employed, analogous to the transfer of excitations from deuterium-deuterium to helium-4 as considered in section 5.3. In reality, however, present knowledge suggests that it is unlikely for a state to exist that is nearly resonant with the donor transitions of interest. The deuterium-deuterium helium-4 transitions with its 23.85 megaelectron-volt energy difference, there remains to be a case even when the tertiary and our higher level types of nuclear molecule configurations are considered, which contribute to the density of states. Consequently, a theory of nuclear excitation transfer where the donor system is deuterium needs to consider scenarios that are more complicated. Here we will in anticipation of later sections, focus attention on aspects of nuclear excited states that are particularly relevant to the problem at hand. In sections 5.7 and onwards, we will describe a more complicated scheme in which excitation is transferred from single transitions to multiple state transitions. This is an attractive prospect because lower estimated side state transition energies tends to correspond to a slower to radiative decay. Moreover, with multiple lower energy states comes to the possibility of combining states and number of the available combinations, and therefore the implied density of states grows rapidly with every state that can participate in such combinations. For this kind of scheme, we care a lot about M2 transitions among the excited palladium stars. Bound says what is currently impeding modeling efforts in the lack of the comprehensive knowledge of bound state level energies, lifetimes, and M2 transition stage, which are needed for more precise predictions of dynamic under this scheme. Consequently, the best option at present is to parameterize the transition range and work with estimates for density of M2 accessible levels. In sections 5.9, we estimate rates for transfer to multiple transitions to anticipate finding. Discussed in that section the very high density of states that results from combinations of even a modest number of M2 transitions suggests that the resonance condition can likely be met this way, especially when the system is a strong coupling regime, as we find is possible under realistic circumstances. While this is a model closer to realistic conditions compared to previous idealizations, we find that unphysically extreme high power transients would be required for the transfer rates predicted by this version of the model to be in the observable range. We also consider an excitation of the nuclear excitation transfer scheme presented above, where we include energy exchange with the uniform, highly excited vibrational or plasmos models. Suppose that there is a polymerized state sufficiently close that a precise resonance can be achieved with the energy exchange. For example, according to the simple nuclear molecule cluster state model, the closest binary cluster states to 23.85 megaelectron volt for excitation from the stable palladium isotopes. Palladium I involves a Ru R-6 plus helium-6 binary cluster states. In this kind of scenario, we can imagine a resonance excitation transfer scheme based on the m deuterium c to the power of 2 minus m helium 4 c to the power of 2 is equal to m palladium star c to the power of 2 minus m palladium c to the power of 2 plus delta np h omega p plus delta n omicron omega omicron plus delta n h omega r, where palladium star is equal to palladium star ru plus 6 helium in 5.10. We will explore how such an additional feature of energy exchange with phonon and plasmon modes affects excitation transfer rates, then considered in combination with the very high density of states associated with the combinations of bound states. If the system is able to make a generalized excitation transfer from one transitions to many transitions starting from the deuterium helium for fusion transition, then it will be able to make general excitations transfer transitions starting from a set of many transitions and going to a different set of many transitions, as long as all of the transitions are in the strong coupling regime and as long as the energies match. Such as system has the potential to exchange energy with optical phonons and plasma efficiently, as long as the magnitude of the relevant all CP transitions matrix elements or optical phonon transitions or plasmon transitions are greater than the average energy separation between the associated multi-transition states. This picture is not only conducive to high rates of nuclear excitation transfer that can outcompete the coherence rates, it also has important implications for the reaction products that become observable from the social process. Reaction products will be discussed in more details in sections 5.14, but we can anticipate already in this section that repeated excitation transfer from sets of multiple transitions to other sets multiple transition can take place in a regime where the density of the states is high, based on the mega electron volt and small differences between states. That exchange of smaller amounts of excitation energy with the coupled phonon and plasmon mode becomes possible, along with where every such excitation transfer. This is especially the case if the interaction is with a uniform optical phonon mode or uniform plasmon mode with substantial excitation, so that the interaction is in the strong coupling regime with respect to the fine splitting between the multi-transition states. This conjecture draws attention to the density of multi-transition states such that energy can be exchanged efficiently. In this regime, when the total energy of the cube system gets into high density of states region, mass energy from the additional deuterium helium-4 fusion transitions during the same current cycle has the potential to be converted to optical phonon and plasma energy as part of the repeated generalized excitation transfer process. Nuclear molecule states with exceptionally long lifetimes that many of them exhibit also play an important role in this picture. They may serve as natural endpoints with comparably high stability where the system arrives after repeated emission of energy into lattice modes. Over time, we conjecture this can lead to the buildup of large populations of particular nuclear molecular states whose eventual decay through tunneling, for example fission, can account for reports of Laused elements production in certain metal hydrogen experiments. Our interest in the palladium stress-bound excited states is ultimately focused on their contribution to the fine structure of the spectrum of multiple transition states. Our interest in palladium stress nuclear molecular cluster states is ultimately similarly focused on their contributions to the fine structure of the multi-transition states and to a lesser degree in connection with a low-level nuclear emission and lousy elements productions. So thank you so much for watching my tutorial video until then. Today is the 8th day of July. Time is near the morning and if there is any simulation for this literature, you can find it from github.com/masterscript, gitlab.com/kashi script, or it's github.com/safra script.